we couldn't have imagined the work going better. The identification of a novel class of polymers which resist bacterial attachment in our experiments and potentially in very different environments is an achievement which we're extremely proud of.
The interaction between the bacteria and the materials isn't really understood. So for us to find a new material that resists bacteria, we needed to cast our net wide, so to speak. We needed to have a big range of materials that we could choose from. And that enabled us to test materials that the bacteria interaction is completely unknown. And in doing that, we were able to find some new materials that had some properties that people wouldn't expect from the current understanding. And in doing so, we've also broadened the understanding of the way that bacteria interact with materials. Each one of those spots is a unique material with a unique chemistry. So on this particular slide, which is 75 millimeters by 25 millimeters, we have 400 unique materials represented. It's a 20 by 20 array, and we repeat that in triplicate so that we can test the reproducibility of the materials. That means that on this one glass slide we have 1200 materials.
Our materials work by preventing bacterial attachment to their surface. And that contrasts with materials which are currently in the clinic, such as silver, which kill bacteria.
The polymer, we don't really know why bacteria hate, but obviously this material, bacteria just doesn't like it. So under the microscope, there's no bacterial attachment. But compared to the glass or silicone normally used in the hospital, bacteria attach to glass or silicone dramatically. So you can feel the bacteria just love the glass. They hate our material, but that's a good thing.
And we hope that that means that the bacteria aren't going to develop a resistance as they do to antibiotics, for example. And the anti-attachment mechanism, the way that works, is that the bacteria aren't allowed to attach to the surface and therefore form biofilms, which are very resistant to being cleared by the host immune system. Instead, they are left swimming in a planktonic state where they are accessible to the immune system, which can clear them as it would do if the medical device wasn't there to allow the biofilm to form.
The data set itself is huge, so we can't use conventional methods to analyze the data. So we had to use a method called multivariate analysis to analyze such a huge and complex data set. And then we had to use this multivariate analysis to correlate to different data sets. And one data set is the chemical physical properties of these hundreds of polymers. And another data set is the bacterial attachment on these polymers. At the beginning, we did not know whether we were going to find any correlation or not. And by the moment we did find a correlation, that was an exciting moment.
We've tested in the lab, in vitro testing, and that was very successful. We took the step of moving into animals, which is often where prospective therapies and materials fail, and we were very pleased to find that the materials did prevent the biofilm formation, and that did allow the animals we were testing the materials in to clear the bacteria. Now we have very good in vitro and in vivo data. The challenge is to have the materials recognized by the medical device industry such that they can be applied widely, and that is going to require us to manufacture the materials in an environment designed for medical device production. There's a lot of potential in human health, but we need to prove that. That's the stage we're at the moment.